Hello and welcome to our class. We are going to study the applications of calculus, so let's get started with history. The rules for calculus were first laid out in Leibniz' 1684 paper. A new method for maxima and minima as well as tangents, which is impeded neither by fractional nor by irrational quantities, and a remarkable type of calculus for this. A very long name. Leibniz started with subtraction. That is, if x sub 1 and x sub 2 are very close together, then their difference, delta x equals x sub 2 minus x sub 1, is very small. He expanded this idea to say that if x sub 1 and x sub 2 are infinitely close together, but still distinct, then their difference, dx, is infinitesimally small, but not zero. This idea is logically very suspect, and Leibniz knew it. But he also knew that when he used his calculus differentials, he was getting correct answers to some very hard problems. So he persevered. Leibniz called both delta x and dx differentials, Latin for difference, because he thought of them as essentially the same thing. Over time, it was become customary to refer to the infinitesimal dx as a differential, and reserving difference for the finite case, delta x. This is why calculus is often called differential calculus. In his paper, Leibniz gave rules for dealing with these infinitely small differentials. Specifically, given a variable quantity x, dx represented an infinitesimal change in x. Differentials are related where the slope of the tangent line to a curve. That is, if y is f of x, then dy and dx are related by dy equals slope of the tangent line times dx. Leibniz then divided by dx, giving this: dy over dx equals slope of the tangent line. The elegant and expressive notation Leibniz invented was so useful that it has been retained through the years despite some profound changes in the underlying concepts. For example, Leibniz and his contemporaries would have viewed the symbol dy dx as an actual quotient of infinitesimals, whereas today we define it where the limit concept first suggested by Newton. As a result, the rules governing these differentials are very modern in appearance, such as the differential of a constant equals 0, the differential of z minus y plus w plus x is equal to dz minus dy plus dw plus dx, and the differential of xv is equal to x times dv plus v times dx, and so on, such as when a is an integer, the differential of x to the ath power is equal to a times x to a minus 1 times dx. Leibniz states these rules without proof. He said that the demonstration of all this will be easy to one who is experienced in such matters. As an example, mathematicians in Leibniz's day would be expected to understand intuitively that if c is constant, then differential of c equals c minus c equals 0. Likewise, differential of x plus y equals dx plus dy is really an extension of x2 plus y2 minus x1 plus y1 equals the x2 minus x1 plus y2 minus y1. Now, let's introduce the Leibniz approach to the product rule. The explanation of the product rule using differentials is a bit more involved, but Leibniz expects that mathematicians would be fluent enough to derive it. The product P equals xv can be thought of as the area of the following rectangle, like this. So this the orange one, and this part, the length of this part, x, the length of this part, v. So the area of this orange rectangle is P is xv. When x increase dx and v increase dv, then the change of the area dp will be equal to this change plus this change plus this change. So the increment of p can be divided into 3 parts. All this can be seen as the L-shaped region in this one. And by dividing the L-shaped region into 3 rectangles, we obtain that the derivative of xv equals x, here, x times dv, that means the area of this part, plus v times dx, that means the area of this part, plus dx times dv. Even though dx and dv are infinitely small, Leibniz reasoned that dx times dv is even more infinitely small, or we say quadratically infinitely small, compared to x times dv and v times dx, and then can thus be ignored, leaving dx dv. Then we have that the differential of xv is equal to x times dv plus v times dx. That means these 2 rectangles. You should feel some discomfort at the idea of simply tossing the product dx dv aside because it is comparatively small. This means you have been well trained and have thoroughly internalized Newton's dictum. The smallest errors may not, in mathematical matters, be scorned. It is illogical and untenable to toss aside an expression just because it is small. Even less so should we be willing to ignore expression on the grounds that it is infinitely smaller than another quantity which is itself infinitely small. Newton and Leibniz both knew this as well as we do. But they also knew that their methods worked. They gave verifiably correct answers to problems which had heretofore been completely intractable. It is the mark of their genius that both men preserved in spite of the very evident difficulties their methods entailed. Now, let's see Newton's approach to the product rule. In the Principia, Newton proved the product rule as follows. Let x and v be flowing quantities, and consider the rectangle R whose sides are x and v. R is also a flowing quantity, and we wish to find the fluxion at any time. First, increment x and v by delta x over 2 and delta v over 2 respectively. Then, the corresponding increment of R is x plus delta x over 2 times v plus delta v over 2 equals xv plus x delta v over 2, and so on. Now decrement x and v by the same amounts. Then we will have the similar expression. Subtracting the right side of equation 1 from the right side of equation 2 gives that delta r equals x times delta v plus v times delta x, which is the total change of r over the intervals delta x and delta v, and also recognizable the product rule. This argument is no better than Leibniz, as it relies heavily on the number 1/2 to make it work. If we take any other increments in x and v, whose total lengths are delta x and delta v, it will simply not work. You can try it and see. In Newton's defense, he wasn't really trying to justify his mathematical method in the Principia. His attention there was on physics, not math. So he was really just trying to give a convincing demonstration of his methods. You may decide for yourself how convincing his demonstration is. Notice that there is no mention of limits of difference quotients of derivatives. In fact, the term derivative was not coined until 1797 by Lagrange. In a sense, these topics were not necessary at the time, as Leibniz and Newton both assumed that the curves they dealt with had tangent lines, and, in fact, Leibniz explicitly used a tangent line to relate two differential quantities. This was consistent with the thinking of the time. Both Newton and Leibniz were satisfied that their calculus provided answers that agreed with what was known at the time. For example, that the differential of x squared is equal to 2x times dx, and the differential of x cubed equals 3x squared dx. Results that were essentially derived by others in different ways. Alright, that's the beginning of calculus. Although it was not that formal, it was very useful. In calculus today, we need the concept of a limit to make it formal and avoid logic error. We're going to discuss more applications of calculus in the following classes.